Hello and welcome to the week 1 segment 2 of Applied Accelerated Artificial Intelligence course. So in this segment we'll talk about the memory hierarchy, where exactly the data stays, the RAM, storage and data movement, which is very crucial because data is being moved from your memory to caches of your CPU as well as GPU. I mean, where exactly you are transferring the data to, how data flows from disk to compute units. So exactly what is the performance gain of using different techniques or different interfaces during this flow, and why this journey dominates AI system performance, we'll talk about today. After this segment, we'll learn the full mapping of the data movement path from the storage to the GPU compute core. One such storage is NVMe, non-volatile memory. So we'll talk about this. Also, we'll see how to quantify the bandwidth and the capacity at each level, because if you zoom out, you will see there is several levels of memory hierarchy, right? So exactly what are the levels performances and how this affects the entire performance of the AI workload. We'll explain with the different state of the art techniques or technologies that are available, like HBM, high bandwidth memory, and why it is critical for AI accelerators. So nowadays HBM or high bandwidth memory is an integral part of AI workload, especially for AI training, okay? Be it LLM or any deep learning models that you see, which require high bandwidth memory for deployment in both the training and inference pipelines. So we'll understand this system or the technology behind this. We'll also identify the bottlenecks of DataLoader pipelines. DataLoader is one such let's say library that we usually use while we load the data from the memory to the compute unit and apply pinned memory optimization. So we will not go into the deep details of memory optimization from the code's point of view, but we will learn from the system point of view for this week, and essentially in the subsequent lectures we'll exactly see how to exactly pin by the different coding methodologies and techniques that are available from different libraries. We'll describe NUMA, which is non-uniform memory access, which affects in multi-socket AI servers. So when we talk about the AI deployment, we talk about AI deployment from the both training and inference pipeline point of view. So usually the training pipeline is deployed in the server grade CPUs. So we'll talk about such example of multi-socket AI servers which are usually used for that particular purpose. So we all know DRAM, dynamic RAM. What exactly dynamic nature? So dynamic means we store each bit into the capacitor of the DRAM. So DRAM cell, each cell holds or each cell stores one bit by the capacitor, right? So it gets leakage over time. To get rid of that or to store further, usually the refresh counter or refresh controller is there to refresh the capacitors to hold the store or hold the bit which we are storing in the capacitor, basically. Okay, so that is the main technology behind that. But here we need to understand the refreshing of these cells happen invisibly in the back end, but this induce time, right? So usually it takes around 64 milliseconds to get refreshed, right? So that actually increases or adds to the latency of the memory accesses, right? So that we need to understand, okay? So that's why the DRAM fundamentals talk about the refresh times when we talk about the cells which are holding the charge in the capacitors. So DDR technology, which is double data rate, DDR stands for double data rate technology. So this technology brings into something which is called dual rate. So what is double or dual data rate? So that means it transfer data both in clock cycle, positive clock cycle, as well as the negative edge of the clock cycle. So in the both clock edge, it can transfer the data. So that's why it increases the bandwidth and hides the latency that is consumed by the refresh rates that are usually happening before or the earlier technologies of the DRAM, right? So this is the dynamic nature of the capacitor based cells. It must refresh at every 64 milliseconds, and double data rate transfers both rising edge and falling edge of clock. So essentially it increases the bandwidth. So our main goal is to get more and more bandwidth, right? So because you saw the arithmetic intensity is basically how quickly we can get the data so that we can increase the performance or effective performance, right? So that is why we need to have increased bandwidth, and we are trying to see what are the different technologies that are available for improving the bandwidth in the memory hierarchy, right? So DDR5, which is introduced in 2021, so since then it's very popular. So we are living in DDR5 generation, which has around, let's say for this example, DDR5 which is 4800 channel DDR5, which gives around 38.5 to 6400 channel will give you 51.2 gigabytes per second per channel. Okay, so that's the improvement that we get using this DDR5 technology. Okay, so you can imagine usually the EPIC processors that we talked about, 9654, right, AMD EPIC processor, they use this 12 channel DDR5, which improves to or gets or attains the peak performance of 614 gigabytes per second bandwidth. Okay, so peak bandwidth it achieves around 614 gigabytes per second, okay, or GB per second. So this technology DDR5 improves the bandwidth, which in turn helps to achieve better performance in AI training, AI model inference, AI deployment. Okay, in the mobile technology, in the mobile and edge technologies, LPDDR5 is used, such as LPDDR5X, which is around 8533 such series is there, M series, which is widely used in NVIDIA Jetson kind of devices, right? Another example is Apple M2 Ultra, which is per channel. So total bandwidth, unified bandwidth, it gets around 800 GB per second. So 800 Gbps is very good. You can imagine 450 or 460 Gbps bandwidth you are getting from DDR5, whereas Apple M2 Ultra is providing you 800 Gbps, which is far greater, almost double, right? So LLM training or the large language model training, such training will be easier in the Apple chips, right? So this is just for one of the reasons for that. Okay, in addition to this increased bandwidth, we also have ECC, which is error correcting codes, applicable or deployed inside these memory hierarchy systems, which can correct single bit errors. Double bit errors also can be detected automatically. So these error correcting codes are also essential in the memory system, because AI is basically training with large data sets. So bit flipping silently will do the data corruption. Okay, so in the long term training, or when the training is running maybe weeks or days, so it's very critical that you maintain the correctness of the data in the entire memory system. So that's why ECC is very important in such systems. And although it brings some overhead, but that is completely fine, around 2 to 4% performance overhead it brings, but it's non-negotiable in the AI workloads. So you cannot just evade, or you cannot ignore the ECC in the system. So in addition to the bandwidth, we have also the overhead, which is basically coming from the ECC part, or error correcting code running inside the memory systems. So as I said, HBM is a game changer for accelerators. So HBM is the high bandwidth memory that we said. HBM stacks multiple DRAMs vertically on top of each other on a silicon interposer. You can see here in this diagram. So along with the GPU, we have the interposer, which is basically stacking or on the same die or same chip. Essentially these are basically your dies, which are here is your base die, die 1, die 2, die 3, die 4. So they are stacked on top of each other by using these metal pods, which works as through silicon vias, right, TSVs. So they are connected. So they bring almost around 10 times larger bandwidth than the DDR5 that we used in the previous technology. So the modern GPUs, which comes with the HBM, so you can imagine that HBM3 coming with H100, which is the Hopper architecture that we talked about, which is one state-of-the-art NVIDIA GPU, which brings around 3.35 terabyte per second bandwidth. So in place of 800 Gbps, now you have 3350 Gbps. So 3.35 Tbps is around 3350 Gbps. So around 4 times more bandwidth you are getting using this HBM technology, right? Obviously the capacity that does not matter, but the bandwidth matters. Okay, how faster we can transfer the data. Similarly, H200 on the other hand, the more modern NVIDIA GPU with HBM3E, this brings around 4800 Gbps bandwidth, and so on and so forth, right? So you have different technologies. So based on that, you get this bandwidth, right? So what we will do with this bandwidth basically, and this bandwidth will result into the memory hierarchy that we will see here, right? So where exactly your data stores? So when we talk about the bandwidth, so bandwidth means what? Bandwidth means this much memory or this much data is being accessed from the memory per unit time, right? So this is the bandwidth, GB per second. This much of GB, 3000 GB per second we are accessing from the memory, right? But what exactly the memory technology that we are using in the entire hierarchy? Let's zoom out and see. So how this bandwidth will transform into the actual storage that we have. So HBM is one technology which is the interface, right? So which is basically giving you the flexibility of accessing this much of bandwidth. But where my data stores or where my data stays in the hard disk, let's say the earlier generation hard disks, which are spinning drive, right? So HDDs gives you access time around 150 megabytes per second, MB per second, Mbps, 150 Mbps. So what exactly you will use this for? We'll use this for the cold data to be stored. This is very cheap in the storage segment, right? So buying several thousands of GBs, several thousands of TBs will not cost you much. So essentially you will use that for your cold storage, which data you are no longer using basically. I mean, it's cold, which is archived data. In the SATA SSD, the solid state drive, which is using the SATA port, which is having around access time of 550 megabits per second. So Mbps of 550 Mbps. So which is sequential, which is good for warm data staging buffers. For that we can use that for data staging. Okay, so this is good. On top of that, if we go higher in the hierarchy, we have NVMe. NVMe is the non-volatile memory. Then the different series are there. NVMe SSD on PCI 4. PCI again is another interface which we can use to mount your NVMe SSD, which gives you around 7 gigabytes per second. So 7 Gbps. So 7 Gbps in place of, so same SSD technology that you are using for your memory, but you are now using NVMe on PCIe 4.0, which gives you 7 Gbps in place of around 500 Mbps if you use SATA SSD. Okay, so the common SSD in your laptop or desktop, which is to mount your SSDs. On the other hand, you have NVMe RAID, which gives you around 56 Gbps of data access latency. So now you can see the gap is essentially slowly closing, and we get around 3000 Gbps in the HBM3, right? So consider a typical ImageNet training job. Okay, we are training ImageNet. So ImageNet, you know how many images are there? 1.2 million images are there, roughly around 150 gigabytes, 150 GB of total. So if I want to train using ImageNet dataset a model which is which needs to access 150 GB data in every epoch means we have to access all the data. So we have to go through, or we have to traverse through all the data in one epoch of training. So at 7 gigabytes per second, let's say I am accessing, right, 7 Gbps. So I'm keeping the ImageNet data set inside my NVMe SSD in the PCIe 4, and we are accessing by using 7 Gbps from NVMe. So that takes around 21 seconds per epoch. So your each epoch will take 21 seconds just for your data transfer, the IO operation. Okay, compute is separate. So if you are doing your computes in minutes, 21 seconds is fine for your IO, right? So which is fine for large models where your compute time is per epoch is in minutes. Okay, this is fine. But imagine if you are having, let's say, multiple GPUs trying to get data from this NVMe SSD mounted on PCIe 4, 7 Gbps. Will you be able to give data to all the GPUs? Let's say 8 GPUs are accessing the same memory, may not. Okay, so these are the different parameters that we need to keep in mind. Okay, so and also when we are talking about AI workload, what exactly the workload means. So here in terms of memory, I mean for each epoch I will need to load around 150 GB of data. Okay, so now you imagine the system that you will be working with, right? Yeah, so the same example, like typical ImageNet training with around 1.2 million images, 150 GB, we need more than 3 GB per second to feed 8 GPUs to be able to compute that in the same time, right? So that's where in the workload definition in the pipeline, or where you are doing the coding for the AI workload, let's say PyTorch we are using for DataLoader definition. So number of workers that we need to define, how many controls that we are defining for the number of workers. So usually the thumb rule, so these are just for example that we are using to relate with the GBPS that we have just talked about. Number of workers is equal to 2 to 4 times number of GPUs that we usually use. And pin memory is true, we need to pin the memory for CUDA transfer. So these basics of CUDA plus how GPUs access the memory and how this pin memory works from the, or translates from the code to the system, that also we will see, but these are just for an example. So when we talk about multiple such systems, we need to think about no longer the unified file system. So we need to think about now the data storage which is distributed, right? Like NFS, like GPFS, which is IBM's large scale distributed database system, data storage system, Lustre. So these are the different parallel file systems that are ideally used for HPC clusters and Slurm environments. Okay. Similarly, for AI workloads, we usually use, there are obviously different ways to segregate the data for data training, but usually vast data or DDN exascalar. So these are Weka FS, these are ideally built for your AI training for high throughput gain for distributed systems. Okay, GDS is one such storage which is designed by NVIDIA, GPU Direct Storage, or GDS, which bypasses the CPU, and basically it takes the help of DMA or direct memory transfer. If you have heard about this in your maybe architecture course or organization course, you will be able to understand the DMA can do the or perform data transfer without the help of the CPU. So DMA can be used also directly to access data from NVMe to your GPU memory, and GDS do that. Okay, so GPU direct storage used by NVIDIA usually bypasses CPU for data storage or data transfer from the NVMe to GPU memory. Now we are talking about multiple distributed systems, and when we talk about these server grade AI machines, we have to talk about this NUMA architecture, which is non-uniform memory access, because now we no longer have a single unified system, rather we have multiple sockets, where these multiple sockets houses multiple such GPUs you can see here, and each will have dedicated DDR5. Okay, so dedicated DDR5 socket, and each socket will have its cores. So you can see that it has 96 cores. This socket one also has 96 cores, and these are essentially linked or connected with high speed inter-socket connection, which AMD calls Infinity Fabric, and the Intel calls it UPI Fabric. Okay, so if you come across these terms, it's absolutely fine, because you just now know exactly what they are. Because when you read these white papers for these architectures or the systems, you will come across these terms. Basically UPI is basically nothing but the inter-core or inter-socket link between the different sockets that houses multiple GPUs and multiple such cores, and each socket will have dedicated DDR5. By the way, one such example is DGX machine. DGX machine uses this 8 GPU system, where you have 2 sockets, and each socket houses 4 such GPUs, and you now know exactly how they are connected. So essentially you have one such NUMA architecture is AMD EPIC system, uses NUMA internally, even if we using a single socket, then also it uses this CCX or CCD topology for your housing of cores and the DDR and the GPUs. So in DGX H100 system, which is multi GPU server, which houses 2 CPU sockets, each with 4 GPUs attached via PCIe switches. Okay, so each will be connected with obviously NVLink 4. Okay, and GPUs 0 to 3 will have to be housed into the socket 0, and 5 to 8 will be socket 1. And now if you see this entire system, why I am talking about this NUMA architecture, because now you see exactly where these cores are, right? So these cores, so if we are running my data loading inside my socket 0 in some core, and we are running the training inside GPU 5, that means this is in another socket, right? So that means I need to transfer the data. So that means I will need some additional time to transfer the data from one socket to another. So exactly you need to know where exactly you are pinning your data loading, where exactly you are pinning your training pipeline, and so on and so forth. So this is an example, very good example, to see exactly where to be housed or where to pin which workload in your system. And if we have data offloading or data loading by using CPUs or cores in the socket 0, and I'm pinning my training into the GPU 4, it's fine. I mean, it's in the same DDR5, right? They will be sharing data from this DDR5. So I mean, we will not have any additional data transfer from one socket to another socket. So that we will be able to know at the runtime. I mean, that in the coding time we have to pin them. Okay, so that is exactly what we need to keep in mind. So that's why we talk about the systems first before deployment. So in summary, DDR5 will give you around few Gbps. Now if you increase the channels in the DDR5, this is per channel. So EPIC system uses 12 channel system DDR5, which attends to 460 gigabits per second per socket, and then you have this NVLink 4 in the H100 which is bidirectional GPU to GPU connection. So this is exactly what I was showing. So each GPU per socket is interconnected with this NVLink 4 data connector, which is bidirectional. That means they can take data, send data, and that can happen at the simultaneous time. So basically it's around 900 Gbps bandwidth it achieves, and then PCIe Express will achieve around 128 Gbps bidirectional CPU to GPU. So the HBM3 will attain around 3000 Gbps, which is GPU on chip. Okay, so now you know different hierarchy of systems. So I have communication from CPU to GPU, GPU to GPU, and I know exactly how much bandwidth I will get while communicating from CPU to GPU, CPU to DDR5, GPU to GPU between GPUs, GPU to DDR5, GPU to HBM or NVMe to GPU, and so on and so forth. Okay, so here is the few things that we need to keep in mind. Okay, data movement matters. Moving 1 byte across PCI Express bus costs around 700 picojoules of energy, and if you use that in compute, so floating point 32 MAC operation on chip will cost you around 1 picojoules. So 1 picojoule and 700 picojoule just to transfer the data through this PCI bus. Okay, so you can imagine around 700 times energy we are spending for transferring the data only to the compute unit from the memory. Okay, H100 peak compute, you know, this we talked about. So the system bandwidth, so if you see the peak compute, so this is the petaflops, 3.9 petaflops in terms of floating point 8. So in this first lecture itself we have used FP32, FP16, FP8. So all are different data types. Okay, and those are all floating point data types because we are talking about floating point operations, right? So floating point operations. So this is your compute performance and this is your bandwidth. So you can see that there is your 30,000 times gap between the data transfer and the compute. So we need to optimize the AI system for data movement, not the compute. Okay, so that's why there are many techniques to optimize the data movement between the memory and the compute units for GPUs, CPUs. So operator fusion, tiling, gradient checkpointing, prefetching, all the different techniques for your data movement optimization. Okay, so we will see these are the different techniques. In practice, for an example, the vanilla attention mechanism, if you see in the transformer models, they use order of n square data fetches, right? So if you have 2048 sequence, data sequence to be processed, so 2048 into 2048 tiles to be fetched per sequence computation. In terms of flash attention, we can reduce that data movement by 3 to 5 times lesser data movement through HBM access. Similarly, gradient accumulation, mixed precision uses also by using reduced computation precision also reduces the data movement. So all the different data movements that are available. However, the free lunch for the compute is over, and the next frontier is memory efficient algorithms. How you are optimizing the memory reduction or memory optimization, memory fetches, the data movement from the memory to the compute unit. So algorithmic improvement, your data movement, different strategies, different optimization techniques. So these are the things that are even more important than just working on the compute or increasing the compute facilities or compute, let's say, capabilities of the system. So with this we'll summarize. Memory hierarchy spans through DRAM to NVMe, and you have seen the different access latencies. Also on-chip bandwidth is higher. On-chip means HBM is higher than the off-chip, which is DDR5. NUMA topology we have seen. We have seen the DataLoader optimization, data movement also we have talked about. So all these will actually be emphasized in the upcoming sessions. You have learned the system, and also we will talk about the different other system based components in the first week, and we will conclude the first week session. Thank you.